Okay, let's start now. So week 12 is not too much content. Very specific contents are there. More. So main topics are there: correlation matrix, covariance matrix, and the next is positive definiteness. The spectral theorem is again is just recall there. There is a DFT. Okay, and these topics are there. Very not so many lectures are there. Only 6 lectures are there. In that, 5 lectures are the topic. The important topics are there. 6 is for practice. So let's discuss quickly because not it would be good. So both of you have gone through with the content of week 12.
Sir, not in details because I am doing week 11 now. Uh,
Okay.
just half portion I did.
Okay. Till
Yes,
lecture
sir.
3.
Yes, sir.
Yeah, actually, I will cover only 3 lectures, and then rest 2 lectures tomorrow. Again, we have a session, so we'll quickly discuss there. Okay, and then
Yes, sir.
the uh, the week 12 now going to finish, and now quizzes, not quizzes. In term is going to be okay. So in term is not hard. Again, I will say um, the if you the emphasis will be more on 9, 10, 11, and 12. Question would be more from these. Yes, yes, Sonali. Want to say something?
Sir, actually, in my dashboard, the lecture 5 is
No,
not
you
visible.
are not audible. Okay, one think 1 minute. Now could you see, please?
Sir, actually, in my dashboard, the week 12, lecture 5 is not available in my dashboard.
Okay. This is the week 5 lecture DFT, discrete Fourier transform. It is not there.
Yes, sir, it's not there.
What about Soma?
Sure.
It's for you the same.
No, sir, I have. I
Oh,
have in my dashboard, week 5, lecture 5.
Repeat.
Yes.
So, could you please send the link of this video?
yeah, okay. Let me send you the link. How? Oh,
Yeah,
this video is
this thing, same showing in my dashboard, sir.
okay. What about Soma? Are you able to see it? Could you do that once? Refresh the page and then.
Sir, same to me. This video is unavailable. I
You
now I open it.
okay? Okay. Just a second. Let me just outside. Let me take to the lead. Okay, it will be available. So let's start the uh, Big 12. For the large matrices, okay. So adjacency matrix is in one, no? I think adjoint graph. Okay, okay. Let me tell you that for the large matrices, one thing we can do, we will use the first one property, okay, and okay. Let me take one problem on it very quickly, because problem would be given on uh, it would be given a graph would be given, and could be asked to write the adjacency matrix. So like this is the problem we have, or even let's say this is the problem. So to get that, so this is the graph. Suppose we have this graph we have. So what we can do first, uh, you can make first a table like this. That would be, or maybe if not, a large so matrix would be there. Let's say this is A, B, C, D, E, F, and G is there, and then A, B, C, D, E, F, G is there. Okay. So where is the graph? So A to AB will take 0 because we'll not consider A to A as edge between them. So where is the edge? So see, these are the vertex we have: A, B, C, D, E, F. And these are the uh, vertices we have. Okay, and the edges are connecting them. So if there is an edge, we will write 1 there, and if there is no edge, then we'll write 0 there. So A to A will consider as a 0. Is there any A to B edge? No, there is no A to B edge. Is there any? So we'll take the first A here, and we'll start looking the other vertices quickly. So A to B, then A to C we have, yes, A to C we have, A to D, no, A to A. So there is no direct edge now. It would be connected with the sum. So we can write like others are going to be 0. Now we will take the B vertex, and now start looking where it is. So at C it is the edge is there, and D. So at C it is, you can write quickly 1, and at D it is, and rest all you can fill out as 0. Similarly for C we have A, E, B, D. So means here B is there, D is there, with A it is, and with E it is, okay, and D is there. Yes, for D it is, only it is not with the F. G and H is also there. I just missed that. H is also there. So H is there also. So F, for F we have no, so there is no for F. G, and for H it is not there. Rest all it is going to be zero. So like this, the filling would be there. But the question would be given at must see, here is 8. This is a 8 cross 8 matrix. So this is a too large even. But if it is at most, it would be given 4 cross 4. Okay? At most, it would be given 4 cross 4. Not going to be more than this. And the process is, you can use the trick that if sum of all, one is, we have tricks, right, that sum of all uh, rows are going to be 1, or sum of all columns are going to be 1, that is going to be 1. You can quickly do that, otherwise there is no other method to do. You have to do A minus lambda I, and you have to follow the steps. Generally, the eigenvalues are going to be 1 and 0 mostly. Okay, so you can assume like that. So the characteristic polynomial that is going to be easily factorized. It is not going to be more than. Okay, professor is even not taught more than 3, so you don't expect. If it is there, then it be easier. You can easily factorize it. Okay, the
So,
only
sir,
way it is.
if the characteristic polynomial become of degree 5 or 4, then what we should do?
No, no, no. So no, so it is not going. It, if it is asked there, then uh, it is going to be in GA and PA. Okay, it is not going to be for. But for quizzes and all, for in term, it is not going to be.
Like in GA11, it is becoming degree 5.
So in GA and PA, it is going to be. Yeah, so anyhow, I have to check that using the properties. If not, then A minus lambda you have to do, and the characteristics are not going to be sort of means you can easily factorize and then you get the root of that characteristic polynomial, either to be 0 or 1 most probably. So the one reason is, this is a symmetric matrix. Okay, please remember your adjacency matrix is a symmetric matrix. So eigenvalues are very much sure that we have done, right? We have done the this spectral theorem for the symmetric matrix. What it guarantees, anyone can tell what it guarantees here? What kind of guarantee it gives? A spectral theorem for symmetric matrices. What is the spectral theorem? Anyone can tell of the symmetric for the symmetric matrices? Haven't remember? But it is really interesting. Why? The reason is here you can use in the adjacency matrix. The one reason is this adjacency matrix is symmetric matrix. So if it is symmetric matrix, then we can apply the spectral theorem. What spectral theorem says? It says that eigenvalues should be real, eigenvectors are going to be orthogonal, and the matrix is orthogonally diagonalizable. Okay, so this is what the importance there of there. So we have a adjacency matrix symmetric. So all spectral properties or whatever the result is going to be, that is implemented. So the eigenvalues, eigenvectors are going to be most probably 0 and 1. So it could be very simple. It's purely factorized. Okay, it is not going to be a complex root. Better? Is it clear? So no need to hesitate. If it is going to be a higher degree even, you will surely get some lambda time. So lambda minus 1 whole to the power 2, 3, 5. It's depend on the whatever the degree of the matrix. Whatever the order of the matrix. So spectral theorem, that's why it is taught to understand even. Okay. So like here, if you do for this problem, is actually 8 cross 8. See if you see it. So this is I made it for B. B is not there. For C it is.
Sir, you take an
For,
example of 4 into 4. Then you solve that.
okay, let
It
me take.
will be better.
Okay, okay. Let me take it. This is here. This is A B. Okay, and this is C here, and this is T here. Let's quickly do it here. So A B C D. Okay, this is A B C D. So let's feel the entry. A to A is not going to be there. A to B is there, 0, 1. And A to C is there. And for D, it is not there. For B, B is connected to only A. So this is 1. And rest all it is 0. C is connected to A and D. So A and D. And rest all is going to be 0. And for D, it is only connected to C. So this is 0, 0, 1, and 0. So this is the matrix we have now. You can now erase it if you want. So this is the adjacency matrix we'll get here. So now even we can do a minus lambda I. So lambda I is going to be lambda 0 0 0 0 lambda 0 0 0 0 0 and 0 0 0. So first, if you see it, is there any sum is always going to be 1, or see, one thing is one we can use. If you remember the property, is this following that property, that the eigenvalue eigenvector property sum is going to be the fixed number always, the row sum or column sum. Okay, I think professor taught the row sum. The second property is at any entry you are getting a kind of 1 0, sorry, 0 0 0 some ith place and 0 star 0. Is there any? So both are actually, it is not there, both is not there. Then it is going, in this case the eigenvalue is going to be the number of that whatever the number is there, and the eigenvector is going to be whatever the means if the entry is going to be the some canonical element basis. Okay, sorry, basis element, canonical basis element, but both are not there, so we have to only proceed with a minus lambda I. So let's do it quickly now. This is going to be n determinant of it. So this is minus lambda, and this is 1 1 0, and this is 0. This is again minus lambda 0 0, and this is 1, and this is 0, and this is minus lambda, and this is 0, and this is 0 0 1. Okay, here it is lambda, so minus lambda, and determinant of it. So we'll take the,
Sir,
let's take
fourth column is 0 0 1 minus
here
lambda.
it is 1, sorry, yeah, 0, sorry, 0 0 1 minus lambda, yeah.
Yeah.
Okay. So this is minus lambda,
Sir,
then we'll get a
second
matrix.
column and fourth column, there is 1 0 0 and 0 0 1 0. Can't we write that 1 is
0 0 1 0, now it is there, see.
No,
0 0
can't we write that 1 is one eigenvalue of this matrix?
So here it is for the fourth column you are saying.
Yeah.
For the this one, no, it is not, you cannot write. The reason is whatever the entry is there, this entry should be, if it is the fourth column, no, so this entry should be here, okay, not here. Okay, this should not be here. If it is there, then eigenvalue is going to be 1, and eigenvector is going to be the fourth column.
Okay, sir. Okay.
Okay.
Okay,
But
sir.
here our case is for it is at the third place.
Okay, sir.
So if you see the theorem, that is clearly saying ith column, sorry, ith entry, and the ith column.
Okay.
Ith column, ith entry.
Okay, sir.
So let's expand this. So if we do here, this is minus lambda. So the matrix of the 3 cross G will get here minus 1 0 0 0 minus lambda, and then 1 0 1 minus lambda, and this is minus plus. I'm expanding along the column only because here is 2 entries there, so it will be easier for us. And this is 1. This is plus minus plus, and this entry is going to be plus. And if you remove this, this is going to be 1 1 0 and minus lambda 0 0 and 0 1 minus lambda. This is what we'll get. So determinant of it. This matrix, determinant of this matrix. Oh, here is minus lambda. Now determinant of this matrix you can expand along the only lambda. So this is minus lambda again, and this is going to be lambda square minus 1. Okay, this is the determinant plus and has this one. So this is going to be, we have to expand. I'm expanding along this one. So this is going to be 1, and this is 0, and okay, minus 1, and this is going to be lambda square. Okay, this is going to be just lambda square. So this is now minus lambda square minus 1, and plus this is going to be 0 it is, and this is minus, so this is minus lambda square finally. So this is the characteristic we got, or lambda square you can take common. So this is lambda square minus 1 minus 1. Okay. So I think this is correct, right? Whatever I'm doing, if I'm making some sign mistake, please let me know. So this is the characteristic polynomial. What we will do, we'll equate to 0. So this is going, if we equate it to 0, so this is going to be lambda square. Here it says that lambda square minus 2 is equal to 0. So here lambda is equal to 0, 0. The roots will get here, plus minus. So 4 roots we got, and these are the eigenvalues we have. Eigenvalues are always going to be real. Most probably you will get many times at many places lambda square, which will make easier to factorize it. Is it clear? And the eigenvector is need to ask, so you have to follow that steps now, a minus lambda I and system of linear equation. That is easier now. Is it clear?
Yes, sir.
For irrational values, how to calculate eigenvectors, sir?
Oh, sorry, here I missed that. Lambda I wrote, no? Sorry, here is a plus minus lambda root 2, plus minus root 2. Sorry, and now what we are saying? For irrational number?
How to calculate eigenvectors?
How to calculate eigenvectors?
Like
So you
here
have
we
to do.
got root 2, so
Huh. So why it is? You have this matrix, no? This is the A minus lambda I matrix. If you for lambda, sorry, root 2, I want to get it. This is root 2, 1, 1, 0, 0, root 2, 0, 0, 1, 0, minus root 2, 1, and 0, 0, 1, minus root 2. Oh, I think all are minus
it
actually.
will be okay,
Yes.
sir. Okay, okay, okay. Got it, sir.
Sorry?
Now got it.
Now easy, no? You just need to follow the steps here. Yes, you can easily make it. Means as usual, you are saying it may be the eigenvector contain the irrational number in that also.
Okay, sir.
So let's discuss this week 10. So this is week 11 content. So these are the adjacency matrix. But good to we have discussed at least. So in week 12 we are going to see the uh, correlation matrix and covariance matrix. These two more important question would be asked on based on that line, the eigenvalues, eigenvector. But the thing is that what is going to be there. So in that, if you see, this is not, there is no theorem, so it's better to be discussed here. Otherwise I used to take the slide, but I didn't do, because what is going to be exactly here, it is just whatever is we are going to here discuss. Means here data would be given, some data is, if you don't aware with what the word data means, what he said professor, there would be, suppose you have some electronic system here somewhere. Okay, some electronic system is there, some input you are giving, let's say here is from battery, you are giving some input voltage, and let's say here is some resistance is there, and there is a, let's say there is a bulb also there. Okay, some bulb is there, you are calculating the voltage here. Okay, you have given the input, or you are changing the voltage here one by one, or maybe it is not battery, in place of consistent voltage I am changing the voltage here, and I am okay, so here I am changing the voltage, and here I am noting the voltage, maybe it could be different as I am changing. So mean to say, here is I am giving the voltage whatever here, and this, let's say this is x portion here, and here it is, and whatever I am calculating there. So this is the voltage, this is the input voltage, this is output voltage. So you can say this is a kind of kind of function it's happening, whatever you are giving. So you are giving something, some voltage you are giving, output voltage is different, input voltage is different, it's behave like a function. So data is nothing but it is a kind of input output function, as you used to graph the function, right? If you have a function fx, let's say x square is there, you usually give x value and calculate the fx value. So if you write in a table wise x and fx, which you can say generally y also. 1, this is 1, 2, this is 4, 3, this is 9. This is how the data is generated. So this is called data. Means you observe the pattern, or not pattern. You observe, you just collected the what you are feeding and whatever you are getting. Okay? What you are feeding here in the this electronic system and whatever output you are getting. So that is the data. Okay? This is the data. Whatever something is there and I'm collecting. So these are, you can separately call, these are the vectors. Okay? You can think these are separately as a vector, x vector, y vector. Okay? So x vector or maybe x vector, y vector. You can separately think as, it is a vertically. This is just a vertical. Let's say I'm writing now a data, simple data. Let's say this is 1, 0, 2, 3. Okay? Output I'm getting here in the same system, electronic system. Let's say -1, or maybe minus is not going to be. So let's say 1, and here it is 2, or let's say here it is 0, even the same, and this is 5, and this is 4. So x vector is going to be here 1, 0, 2, 3. Y vector is going to be here. So here, no, one thing is that, so we are considering this is as a vector here, but professor is also considering the same as this one, 2 cross 2 for the 2 cross 2 even. So let's be on that. So there are two things out there. So just a second, let me confirm that how professor is considering the vector. So even no need of it. Okay, it is, I am just from my side I am saying. So see, he is considering the vector as x1 and y1. So see, he is saying the data, this one. Okay, he no. So considering not x1, see, as I am considering the vector. So he is considering x1, x2, x3. This is a vector y1, y2, y3. Okay, so these are the vectors we have. Okay, yeah, we can consider these. This is x vector and this is y vector, which is 1, 0, 5, 4. This is the vector we have. Now there is once we have a data, then there is statistics. Generally, we know the statistics term will come. So all of you from maths backgrounds, you know a bit about the mean, median, mode. These things are there. Okay. So like, what is here? The if we denote the vector x as the collection of left one, the y vector is as this one. So there is a thing that correlation between these two vectors. So before to start even correlation, there is a, so even let me say the professor even started from the correlation thing. I will, so even let me say the, what is it? Correlation is nothing but if you think in the linear algebra. Okay, so correlation is, you can say, we have studied now the inner product also. So we have this vector, we have this vector. So correlation, okay, correlation is nothing but the dot product we have, right? Or inner product between these two. We have studied the inner product upon the norm of the separate vector. This is what the correlation between these two vectors. Now anyone can tell what is a correlation, sorry, what is a inner product between these two vectors? Anyone can answer here in this problem? What is a dot product here? Means inner product. Inner product is nothing but a dot product. What
Sir,
is the
1
dot
into
product?
1 plus 0 into 0 plus 2 into 5
23.
into 4.
Yeah, so the dot product here, it is going to be 1 into 1, 1 is square. So here it is 0, 0, 0 square, plus 2 into 5, and plus 3 into 4. So if you squaring with this is 0. So this is going to be 10 and 12. This is 123. Okay. What is the norm of this vector? What is the norm of this vector? Norm of x?
Root 10.
Root, root 10. No, it is going to be more than this.
Sorry, sir.
1, 1
14,
plus
root
4
14.
plus 9, 13, 14. So root norm is going to be root 14. Similarly, we can calculate the norm of this vector, which is 1 plus 25 plus 16. So this is 41 to 42, root 42. Yeah. So see, the correlation is now just substituting on the formula. Correlation is nothing but between the, so if data is given, ask for the correlation is denoted as RXY, normalized correlation. Here it is. Generally correlation will say, we say it. So dot product between them. So we are now algebra doing. So before to doing this part, okay, place of saying to be this part, better to say in the linear algebra case, dot product between the vector and the norm of the vectors divided by the norm of the vector. And this is one Cauchy-Schwarz inequality. By the Cauchy-Schwarz inequality, it says that it is going to be between 1 and minus 1 at most. So here XY is this the normalized correlation. Let's say this is a correlation. So correlation is 1 plus minus. So if only if this is going to be, so means here correlation is, so it is as the formula here it is given that it says that correlation, it is going to be correlation when your vector x and y, or maybe the case is that the data, whatever, if you plot, we can plot data, right? It is going to be at most this case. The correlation is going to be 1 plus minus 1, then it is going to means y is equal to c time x, then it is going to be. So can you answer the, is this correlation is 1? Without, just now we discussed, is this correlation is 1 between the correlation between the data here x and y?
No, sir.
Reason is y is not actually some c time. Y is not this is 5, no? 5 is, you cannot easily get c time some c time x. It's going to be some different. 2 time it is not there. So correlation in that case. So here is no, this correlation is going to be at most plus minus 1 and minus 1. This is what it is. Now before to start, so this is the correlation. This is, you have a data, and this, you have seen that this is a correlation. Now there is a, before there is a covariance matrix. Before to covariance matrix, there is a mean is there. So let's discuss first, then covariance matrix will discuss. So again, if you have a data is given, so here is, will not data, will not consider the data. Here is, will not say, let's say I have this, some numbers is there. Okay, some numbers is there. 1, 2, 3, 4, 5, 6, 5, 5, 6, 7. Some number is can the given is there. So what is the mean? Mean is nothing. So there is one mean. Mean is nothing but, no, you sum them all and divided the number of the data here. Number, whatever the number is there. How many numbers are there? So if you sum them all, just sum them. Okay, these are the xi. You can say x1, x2. Till this is 1, 2, 3, 4, 5, 6, 7. So xi, sum them and divide by the number of. This is your mean. This is called mean of this data. So it is, let's say this is x is there, so you can say even a small x, then mean is going to be x bar. Okay. Now next is there is a variance word. There is a word variance. What is a variance? Variance is no whatever you have calculated here. This one, no, it is surely, if you see it, it is surely lie between, let's say this is x1 and this is x7. Okay, it surely lie between x1 and, okay, the mean x bar is surely lie going to be between this one. Means whatever the value here, it is going to be at most 1, and here is, sorry, lesser point, lesser side is going to be at 1, and the great at most it is going to be 7. So if you sum them and whatever the mean calculate, no, it will be some between, maybe it is rational number, not exactly the number here it is, but it is going to be the between the range 1 and 7. Okay. So it is going to be 1 and 7. So what it means that, it means that the whatever the mean you are getting, no, so you can think that, or we can think here how far it is going to be from this mean. Ever we think, or ever you thought that, okay, let's say this is going to be some 4.5, so how far the one from 4.5, or mean to say, how far x1 from the mean, how far x1 from the mean, how far x2 from the mean, how far x7 from the mean. So how we can do that? It is, so to know it, it's saying to be, okay, let's divide, or xi minus x7. Okay, sorry, xi minus x. Sorry, xi minus x bar. Means this is this tells you how far it is. But again, if it is giving the separately, for x1, x2, x3, you are calculating the separately how far it is. Can we think about the mean of it also? So if you find the mean of this part, means sum them and then divide by the number of data, and this is called your word variance. This is going to be a single real number. This is called variance. Okay, these are some definitions are there. Okay. So these are important. The reason the case is, it is, oh sorry, here it is, uh, to make it here, no, variance we want always positive, so we have to square them. I just missed that word. This is going to be, yeah, here the case is that here is the same you are saying, this is going to be how far it is, so this is going to be negative. So to exact calculate, we have to do square. The reason is, means squaring is to making the positive. One reason is there, okay, and the second reason is, uh, we want only, it is not affecting much on the how far it is. Okay, squaring any number is not affecting much on the number. You know that, okay, if you do a square of 4, do 2, which is 4, so you know, right, it is a root of, means, or it is a square of 2. So mean to say here, it is not, squaring them is not effective, but we want only the actual thing is that how far it is. So that's why, and we don't want zero or negative value, we want positive. So that's why the reason here it is square is done. Okay, for each distances, no, means how far it is, square them, sum them, and divide by the number of data. So this is called your variance. Okay, so this is one kind of called the spread of the data also, means how far it is. It's tell you if it is increasing, no, that means your, what it means that, suppose your, this number is very large, this number is very large, what it means that these differences are actually very, these single numbers are very large. What it means that your data is very spread out, that's why your differences are actually, you are getting the too much spread. So if it is very large, then your data is very spread out. So this is kind of variance is also called the spread of the data. Okay, different word. This is called a spread of the data sometimes. Okay. So this is one thing is there. So let's start now the correlation matrix. Is this session till 8 or 7? Till 8 it is, right? So how it's depend on how we are able to discuss till uh, are you there, both of you?
Yes, sir.
Yes, sir.
Okay. Okay. So so please, are you able to understand it? What I'm saying, getting it?
Yes,
Yes,
sir.
sir. Yes, yes.
So now, what is a correlation matrix? So we first thought here this case, no, this is a data, this is X portion, and this is Y portion, and whatever here we got. So correlation matrix is we start thinking of this case. Means we will take the x1 y1 both, x2 y2. We also think this is a vector, no, of this case where this is your input output. I'm collecting input output. Why I'm saying this is a different thing. Whatever we just now discussed, the vector is like this and this all. But so here, one thing is that, and we calculate the correlation between the input and output. Okay, so this is a correlation between input and output. Okay, normalized or normalized correlation. This is a correlation between input and output here, x and y. But here now we are calculating the correlation matrix. So here the correlation matrix calculated by number of data. Okay, number of data, and these are we will take one vector. So you can write here like this. The vector it is x1 y1 x2 y2. Okay, so this is the transpose value. No, we want 2 cross 2 matrix. So the transpose should be written here. So if you vector is we generally write like this. This is our vector. I am considering now the vector portion is this one. Okay, or you can say the input output. I am collecting not the case vertical one. Now horizontally I am thinking this as x1 y1, and this is your transpose of it, x1 y1. So let's say this is your u1, this is your u2, this is un is x and y1, x and y1. So by this way you can calculate all. So you can say this is un transpose. So by this way you will get a 2 cross 2 matrix. No, each one is actually 2 cross 2 matrix. This is 2 cross 2 matrix. Each n is 2 cross 2 matrix. You have to sum them all. Okay, you have to know, right? This, if you sum them, this is going to be also a 2 cross 2 matrix. Entry wise sum you will do, and outside 1 by n is there. You can divide each entry by 1 by n. So this is whatever the sum you got, divide by n. Whatever the sum you got, divide by n. By this way you will get a correlation matrix. Okay, this is one thing. The another interesting thing is that no one
Sir,
additional thing we'll discuss, and
sir,
this lecture is finished.
sir,
Yes, yes, yes.
x1 y1, what is the value of x1 y1? That is x number of we have taken the number, that is x1. We have to take
So
first number x1 and then x2, then
no, 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 no. So here it is. Let me write. Let's say here it is going to be your u1 is 1 1. Your u1 is 1 1.
yes,
This
sir.
will give, these two will give you u1. This will
Okay,
give you,
understood. Yes, 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 sir.
and this will give you u3. Okay, this is like the case.
Yes, sir. Okay.
So this is one thing. Now, very interesting. So this is your correlation matrix.
So how do we write this in the form of the matrix, sir?
So writing the
Means
form of the matrix. So here it is. Let me do one. So this is your u1. So correlation for this data, correlation matrix for this data is going to be, your data is 1 1. The first, this is your, okay, let me write, u1 is your 1 1, u2 is your 0 0, u3 is your 2 5. Okay, this is what it is. And u4 is your 3 4. Now the correlation matrix, okay, correlation matrix is going to be 1 by n, 1 by n, this 1 1, and the transpose of it, mean to say 1 by n u1 u1 transpose plus u2
Okay, sir.
u2 transpose. So this is 1 1 plus 0 0, horizontally you will write 0 0, plus 2 5, horizontally you will write 2 5, and the next one is 3 4, so horizontally also you will write 3 4. So see, now each will give a 2 cross 2 matrix. So this one will be a 1 1 1 1 2 cross 2 matrix. So this is going to be 0 0 0 matrix. This is going to be 4 10 10 and 25. Multiply, if you multiply you'll get 2 cross 2 matrix. And this is 9 12 12 16. See, now if you sum them all you will get a single 2 cross 2 matrix, 1 plus 4 plus
N
9.
will be 4 here, na?
Sorry,
N will be 4.
here n will be 4.
Yes.
This is 1 by 4. And now by this entry you can divide each entry by 4, this entry by 4, this entry by 4. So this is your correlation matrix, and ask on this basis it is asked that find the eigenvalues, eigenvector of the correlation matrix. So this is your correlation matrix. There is another matrix, covariance matrix. See, there is a word added, covariance. See, this is a relation. Okay, this is a correlation matrix. See, this is a covariance matrix means what? Means I have to find the variance of each data. What it mean that? So here is my data. Let me erase it. So here it is my data. Okay. What I will do? I will find the separately mean of this x bar. Right. We can write easily mean. Mean is going to be 1 plus 0 for x bar, means for x, for data x. Now you have to think separately here, or I can give you the different idea if you are making the getting the confusion. The case is that you have a data, this one u1, this is our data. Now I'm thinking the same case that this one, this is our u1 u2. So what you will do, you can calculate un mean. Un mean is going to be, you have to sum them all. u1 1 means here u1 plus u2 plus u3 plus u4, and divide by the number of data. Okay, that is what it is. It means that 1 by 4 u1 u2 2 5 u3 3 4. So this is going to be here. If you sum them 1 by 4 you will get here 2 cross 2. So this is no mean I am calculating here of the each vector. So the vectors we have this one, the x1 y1 case, this case, or in this case I am calculating. Okay, and here it is. Now sum them all and it is going to be 1 plus 2, 1 plus 0 plus 2 plus 3, and 1 plus 0 plus 5 plus 4. Okay, now it is you can calculate here, this is 5 and 6. This is going to be 6 by 4. This is 9 and 10, 10 by 4. So this is, you got u mean. You, not un, sorry, u mean. You got u mean. Now what you will do? This is, covariance, no? Variance case, what we have just now learned. Variance case is learn. You have to, the data is given, you have to subtract the mean. Similarly, here is, I have u1, u2 till okay, u3 and u4, and just now I calculated the mean. So what you can do, you have to find the u1 minus u mean. Okay. This is one vector, it is this is, and the u1 minus u mean transpose 1 means whatever, if you calculated whatever the u1 minus u mean, and by this how we calculate the correlation matrix. First to calculate the this vector. Okay. First calculate this vector, and whatever we did here, same thing we have to do, means the vector and the transpose of it. Okay. Plus u2 minus u mean and transpose of it. Are you getting, both of you? Are you getting it? This one? I don't know.
Yes, sir.
Sir,
Uh-huh.
covariance formula, that is summation of xi minus x bar by n, then that is the value.
Sorry, sorry.
Covariance, that variance value.
Variance. Huh.
Then for
This is
covariance,
variance for squaring them. So this is what it is.
okay, then for covariance we have to subtract. This is simple.
1 minute. 1 minute. This is the mean we have. Not we have to subtract it. So subtraction we are doing, no, term
Yes,
wise.
yes.
Term means entry wise we are subtracting.
Okay.
And in place of a squaring, we are doing the transpose.
Yeah. Yes, sir. It is.
Okay.
First and
So could you please do it in a matrix form?
Well, let me do it. So this is going to be plus, and this plus u3 minus u3 sorry, u mean transpose, and the u3 minus u mean, and then transpose of it, plus similarly u4 minus u mean and transpose of it. So that means that let's calculate the first one. So our first one is mean we have calculated. First let me write here, which is u mean is 6 by 4, 10 by 4, 10 by 4. So u1 is our 1 1, u mean our just now calculated u by 4, 10 by 4. Sorry, this is 10 by 4. Okay, this is the, I am calculating this one only, u1 minus u mean, which is 1 minus 6 by 4, 1 minus 10 by 4, which it will give 4 minus minus 2, and this is 4 minus minus 6, 4 by 4. So this is, we got only this one, but we have to do this and then transpose of it. So the final step is to write here. Let me I'm writing here now. So means here minus 2 4, minus 2 by 4, minus 6 by 4. This is the vector and the transpose of it, minus 2 by 4, minus 6 by 4. So this will give a matrix. So this will be 4 by 4, 4 by 16, and this is 12 by 16, and this is going to be 12 by 16, and this is going to be 36 by 16. So this is a matrix you got. Similarly, you have to calculate for this one. Okay, you'll get a matrix 2 cross 2. Similarly this one, similarly this one, and you have to sum them all. So this is a big process, but hope you are understanding, right?
Yes, sir.
Now is it
Yes.
clear? So now once you've calculated all, and just sum them and divide by
This is time consuming very much.
this is time consuming. This is your covariance matrix. This is your, so there is a formula, simple formula. In place of doing this, you can remember a formula. So what is that formula? The final formula is this one. I think professor is wrote somewhere. This is What is that formula? We have calculated the, see, variance. This is your variance. Variance for the data x, variance for the data y, and now you can calculate the correlation between them, and separately the variance of x, variance of y. See, why this way? You can remember the formula. This is your formula. Whatever we are doing here, this is what it is. By remembering this formula, you can covariance square, and this is your correlation one, and the covariance. This is the correlation and covariance. So let me take this screenshot of it. So maybe I will tell you what is exactly here. So with the data case, with the example one. Okay. So what it tells our data is x and y 1 0, I think 2 and 3, 1 0 and 5 and 4 something. This is our data. So what is that? We will calculate the variance for this data, for this the single one x bar. Means here not only say covariance, which is denoted as sigma x, which is nothing but just my we calculated variance for the single vectors. This is what it is. We have, if we have a single vector, we can calculate the variance of it, which is this one. So see, you can use now this data, you can calculate the variance, which is this one. Okay. Similarly, you can these are the numbers you have, you can calculate the variance of this one. Okay. Separately you have to calculate. And the next is uh, the next is you have to find the correlation of them also. We know, right, the correlation sigma rxy, we said. Here is professor is now writing sigma correlation, this one. You have to calculate the correlation between them also. Once you calculated all, then apply the formula. This is your sigma square, this is your this is your sigma x, sigma y, and the correlation between them. These are 10. This is a symmetric matrix anyhow. So this is your correlation and covariance, and this is covariance for y. So each is thing you can calculate now separately and just need to substitute in the formula. So either you can calculate by this way or you can calculate by this way. Both are going to be same. Okay. Separately, either you can calculate or the formula you can calculate. You can. It's totally up to you. Is it clear?
Yes, sir. Second one is little
Yes.
more easy.
Second one, this one is easier, no? But it will take the same time because same number of calculation you will do.
Calculations, yes, sir.
It is not going to be different. Exactly the same number of calculations. If you do the addition, the number of addition,
Yes, yes.
subtraction, square, all same.
Yeah, same number, same time. Okay.
So this is what the correlation matrix, covariance matrix, mean, variance, this all is there. The next is important, positive semi-definite, and interesting topic. Here is again you will see the role of eigenvalues, eigenvector. Just need to calculate the eigenvalues and eigenvectors. So what it is, there is a terminal, it's saying everything. So let me tell you, the first thing is that uh, before to first start it, there is one thing. It is we just now know this correlation. So you can remember it also, or it is it is very much obvious also. This covariance matrix. This is a symmetric matrix. Okay, this is a symmetric matrix. From the formula, it's also you can see how it is. The square is there, but these two numbers are same. Okay, so covariance matrix is symmetric matrix. Similarly, correlation matrix is also symmetric here. calculated this one. This is also a symmetric matrix correlation. So covariance matrix is symmetric, correlation matrix is symmetric. So one thing is there, once we have a symmetric matrix, no, symmetric matrix, so we can think a case is this. The word it is it positive, definite, positive semi-definite, professor is saying. There are so many words: positive definite, negative definite, positive semi-definite, negative semi-definite. There are so many things are there, but professor is only taking the positive semi-definite. Let's be on that. So he's saying positive semi-definite. If you have a symmetric matrix, is this positive semi-definite or not? So one thing is need to note that if you have a square matrix, no, let's say I'm writing here 1, 2, 2, 3. Okay, I have a vector. Let's say not vector. I'm just writing this one, this variable vector x and y. So let's see what it's happening here. I'm writing here x transpose and this matrix A and this x. So let's write this expression. X transpose is going to be this one. Matrix is going to be 1, 2, 3, 4. Sorry, 1, 2, 3. This one, and here is again x. Here it is written. So here I should write capital one. Then it will be visible. Here is x. So this is x and y. See now what I am doing. I have to do multiple. Let's see that how what expression I am getting. Okay. So in the last I will do this final multiplication. Let's do this one. This is going to be x plus 2y, and this is 2x plus 3y. Now the finally if we multiply this, this is going to be x square plus 2xy, and this y is going to be 2x square plus 3xy. X square plus, no, this is going to be 3x square. I think I made a wrongness. Okay, this is, sorry, this is going to be x square plus 2xy plus 2xy plus 3y square. This is how the matrix will multiplication, right? This is horizontally and this is vertically. So you'll get a scalar, right? So this is x square plus 4xy plus 3y square. See, I just started thinking this case x transpose the matrix, symmetric matrix. I took any symmetric matrix and then x it is. And when I did this, I got this kind of algebraic expression: x square plus 4xy plus this one. Okay. And the conic section we have studied, right? A conic is a kind of ax square plus by square plus cxy plus, okay, plus d plus e is equal to f. And when I was taking the session, I said no, just remove this part and think about x square plus by square plus cxy. So this expression, so this is your function is there. Okay, this function, this is a quadratic function. See, each degree is 2. Here is degrees 2. Here is degrees 2. See, here is degrees of variable x is 1 and variable of x y is 1. So that's why degrees of this term is 2. Of degree of this term is 2. So this is a quadratic function. Okay, and not only the quadratic. This is a quadratic form. It is called the each term have degree 2. So we started from here and start looking here, but actually it's started in the newer case. We in when we started studying this quadratic form, it's actually came from here. We first seen the quadratic form and then back to the matrix. Means a quadratic form could be written as a matrix expression form, which is actually collecting the linear algebra case matrix and that. So we don't want to go in these deeps. We don't go these deep. We want only this matrix. if you have a symmetric matrix, is this positive definite or not? This is a small lecture, so we'll not go in so deep. I will just now jump to the exact thing which professor is saying. Exactly what he's saying: if you have a positive, sorry, if you have a symmetric matrix, then is this symmetric is positive semi-definite or not? So what is that? We'll just calculate the eigenvalue lambda 1, lambda 2. If both are positive or equal to 0, then your matrix is positive definite. That's all. Here is only the positive definite definition is professor is what it is saying. If your eigenvalue is positive or it is 0, then your matrix is positive semi-definite. If it is not, then it is not there. There is other things are negative semi-definite, other things are there, but is not saying anything. So we will not say anything here also. If it is there, then we'll say your matrix, symmetric matrix is positive definite. Is it clear?
Yes, sir. Positive definite.
Positive semi-definite.
Sir, that is positive semi-definite.
So our this matrix, this one, okay. I
When
don't know.
when
Let me calculate.
lambda 1, lambda 2 is greater than equal to 0.
Then our matrix is called positive semi-definite.
Okay, sir.
If it is exact strictly greater than 0, this is called positive definite. But he's not telling. He's very specific here. I don't know why he's hesitant to discuss more or lot, because these are just small things are there. Negative definite is there, but he's just saying positive definite. Positive semi-definite. So there is a case actually. Let me add from my side even. If it is strictly positive, both eigenvalues are positive. Okay, then it is called positive definite. Semi word will be removed. The
Yes,
semi
sir.
word added.
I am telling that that is called
Sorry,
positive definite when lambda 1, lambda 2 is definitely positive.
definitely positive. Then it is positive definite.
Yes, sir.
If any one of them is 0, then you can say positive semi definite.
Okay, sir. Okay.
So strictly positive means none of them is 0. Either positive means none of them is 0 means not either. Both are may either could be 1 2, or maybe 3 4, maybe 5 6. If it is eigenvalues of these cases you are getting, then your matrix is positive definite. If you are getting 0 1 eigenvalue as, or 5 0, or 7 0, or 9 0, kind of this one, or maybe 0 0 2, means one of the eigenvalues 0 in that, then your matrix is positive semi-definite. Okay? Okay. That's all in this lecture is very small, and this is what the professor is saying. It is he is not saying anything more. He's just saying when our matrix. So he the proof is saying the covariance matrix CU. Just now we have seen the how it is going to be positive. Covariance matrix positive semi-definite always. He is proving in that. That is what he is saying. Otherwise, he jump to the eigenvalues, eigenvector, and then start saying, okay, your eigenvalues is positive, then it is going to be a positive semi-definite or not. So that's all he is saying. One thing is there. Ever you thought that if you have any rectangular matrix, this is interesting.
Excuse
Let's
me,
say 2
sir.
cross 3. Yes. Yes,
So
yes.
the simple way to find the positive semi-definite matrix is that finding the eigenvalues, right?
That's all. That's all. That's all. Yes. Adding the eigenvalue. If and decide that based on your eigenvalue. Eigenvalue is positive, negative. Based on that, you can say. This is very interesting. If you have a matrix, this is a rectangular. I'm not saying square. This is a rectangular matrix. If you do A multiply with the same transpose one, see this matrix, see the order here 2 cross 3. The transpose, if you do, this is 2 cross, sorry, 3 cross 2. So here the matrix you will get 2 cross 2. Okay, this is your A transpose matrix. Similarly, maybe it is going to be different also, not maybe. If you do A transpose A matrix, which is 3 cross 2, and this is our original is 2 cross 3. So if you do, this is going to be the matrix 3 cross 3. This is A transpose A. See, this is become a square matrix. So this is in square matrix, but one thing is that if you observe it, no, this kind of matrices are always symmetric. This kind of matrices are always symmetric. You can check even. You can give any matrix here, and if you find A transpose or A transpose A, those matrices are always going to be symmetric. Okay. He just discussed that these are things are there, so I am telling also this kind of matrices are all square matrix. But once you we cannot say any for general matrix. Okay, if you have general matrix A, we cannot say is this positive semi-definite or not. We want only the symmetric matrix. If your matrix is symmetric, then we can talk about the positive semi-definite or not. Is it positive semi-definite? If you have general matrix, we cannot say anything. Okay, if you have, let's say I have this matrix 1 2 3 4. See, this is not a symmetric matrix. Somebody's asked, is this positive definite? You can say this question is wrong directly, because positive definiteness word is there for symmetric matrix only. Okay, this comes from this angle only, from here to here. Okay, and these matrices are symmetric here. Okay? This comes from conic, but professor started conic and then he's not saying about that. He's just saying started from symmetric. The next lecture is interesting. Normal matrices. This is just a repetitive thing of whatever you studied in week 11. Okay, if you see it lecture, these are already repetitive. Means here the spectral theorem is going to repeat here. The one separate thing is there in that is interesting normal. There is one extra thing is there. Rest all video is actually same content is there. The separate thing is there, normal matrices. Okay. Normal matrices. What is a normal matrix or normal operator? Okay, so what it is, let's say I have a linear transformation from Cn to Cn. Okay, I have a linear transformation. Say this is a Cn to Cn. I'm talking about the complex matrices. Okay, let's say I have, this is what it is. So we have seen, right, adjoint of the linear operator T star. We have seen that, or in different word, in different say, let's say the matrix representation of T is A and the adjoint is T star. So what is the matrix representation of T star? Anyone?
That's A bar transpose.
A bar transpose means A Hermitian
Conjugate.
generally we call.
Yeah, H.
A Hermitian.
Hermitian, yes.
Okay. So the thing is that here is we call a normal matrix or a matrix or a linear operator as a normal operator when T composed T star is equal to T star composed T. Or in matrix case, A Hermitian is equal to A Hermitian A. Okay, A Hermitian is equal to A Hermitian A. Then our any operator or matrix is called normal matrix. See, it is here. This is what it is. That's all it is. This is only the definition of normal. But very interesting is there is some properties is there. So this is what the definition of the normal matrix. If your matrix, if matrix is given, suppose the matrix is given, said is this a normal or not? So you just need to check A Hermitian is equal to A Hermitian is happening or not there. Okay. Then your matrix is normal, or for the linear operator also. The both expression, the whatever the expression you are getting, both should be same. The very interesting or property, which is I will say the important for the in term also. Okay, the property is that, let's say I'm saying A is a normal matrix. Let me write the in highlighting part. A is a normal matrix. Okay, here you can remember always if and only if. Okay, this is very important. Okay, if and only if eigenvectors, okay, eigenvectors of matrix A are orthogonal. Okay, if and only if your matrix is normal, the eigenvectors of the matrix A are orthogonal. Okay, so if it is for one sided, okay, this is, and this is if and only if is there means both side is there. If eigenvectors of a matrix is normal, sorry orthogonal, then your matrix is normal. This is what it is. If eigenvectors are orthogonal, then you can directly conclude that your matrix is normal. Or if your matrix is normal, then eigenvectors are going to be orthogonal. You know, right? If you have a symmetric matrix, then you know by the spectral theorem what it says. It says that the eigenvectors are orthonormal. Okay. Hope you remember, both of you. You know it.
Yes, sir.
If your
Yes,
matrix
sir.
is symmetric, then a spectral theorem says that your
Yes,
eigenvectors are
sir.
orthonormal.
Yes, sir.
But here is in the normal matrix case, normal. Okay, maybe there are so many words is there, normal, symmetric, Hermitian. But be clear with it that this normal word, normal matrix word, is coming in the week 12. Okay, there is never you have seen this term. You are looking at this term in the week 12. Okay, the normal word, and it says that a matrix said to be normal if the eigenvector of the matrix is orthogonal. So mean to say, let's say I have this matrix, or if u and v are eigenvector, okay, of A, then it is definitely that and the both are orthogonal. Okay. And
That
this
is
is
the
both
dot
side.
product will
Okay,
be zero.
dot product would be zero. That's all it is.
Yes, sir.
Dot product is going to be zero. This is very important. This is, I'm saying, you can see some question from here in the intern. Okay, so be sure with it. So this is what it is, and rest all the other topics are just a repetitive. If you see it, the complex complex spectral theorem, if you see in the week 12, sorry, week 11 also, complex spectral theorem is there in that already, I think, in Hermitian. So same thing is there. What is that? I'm telling you that if you have matrix, so what is the complex spectral theorem? That's why I'm not going to tell more about it. The complex spectral theorem, it says that if your matrix is Hermitian, then let me write that term. If matrix A is Hermitian, no? Hermitian means Hermitian means anyone? Any of you?
KH, sir.
A is A equal to a Hermitian, right? Means a conjugate transpose equal to A transpose.
Yes, sir.
This is what a matrix is called Hermitian. Okay, a matrix is Hermitian. If a matrix is Hermitian, then matrix A is orthogonally diagonalizable. Okay, orthogonally diagonalizable, and not only this one. If and only if and only if. What is there? Means if a matrix is orthogonally diagonal, then the matrix is Hermitian. Okay, and if your matrix is Hermitian, then it is orthogonally diagonalizable. The same theorem it is. Nothing, no changes there. Means let's say this matrix 1 2, or let's say 1 I minus I and 1. See, if you have matrix A, see it, A Hermitian is going to be the same. You do the A Hermitian, this is going to be the same. What is the property of it? If you find the eigenvalue of it, of this, is real, eigenvalue is always real. And the second thing, which is the spectral, gives the guarantee that eigenvectors, if you find it, are orthogonal to each other. Orthogonal to each other means eigenvectors, you have u and v, then u is perpendicular to v. Okay. This is what the complex specular theorem in this lecture it is. So except this normal, everything is of weak 11. That's why even the proof is also the same if you see it. So this is the for the normal case, but rest all once you move ahead, everything of is the same for whatever is in the lecture of week 11. For the operator also, he is saying orthogonally diagonalizable if and only if it is represented in a normal matrices. Okay, so he is saying uh, okay, so complex spectral theorem is he is using this definition also, interesting definition. So here is he is saying this different definition is not different theorem, both are actually meant to say same, because it is indirectly he is saying the. So I said one theorem, no, this is was complex spectral theorem I said. So this is so he in place of this is a spectral theorem, Okay. If he is saying complex spectral theorem, so let me name it out here. So the complex spectral theorem is. So I just so let me say that I made a mistake. I'm not making a mistake here. These naming convention are same. Professor is stating differently. Okay. So naming convention mean to say the spectral theorem, complex spectral theorem, all are actually same. But professor here uh, is in a different. He is saying two different things. So let's be on that only. I want to be also on that. So what is the complex? I just now discussed the just spectral theorem. Okay, I just discuss just spectral theorem. A is Hermitian, then it is orthogonally diagonalizable. He is saying the complex spectral theorem for the normal matrix. Okay, now also we are looking for the normal matrix. So he says that if your matrix diagonalizable, if your matrix is orthogonally diagonalizable, then your matrix is a normal matrix. So this complex spectral theorem is for normal matrices. Okay. So if I will write a spectral, so let me make the spectral theorem. Okay. Spectral theorem are there for symmetric matrix. Okay. Spectral theorem is there for Hermitian matrix. Okay, and there is a word I'm adding extra, complex spectral theorem for normal matrices. Okay, is this clear? All of you, so both of you able to distinguish now at least? Spectral theorem for
Yes.
symmetric, spectral theorem for Hermitian,
Yes,
complex
sir.
spectral theorem for normal matrix.
Normal
Okay, there is word
matrix.
added, complex word is there. What it says, that it says that normal matrices are also orthogonally diagonalizable. Okay, or if a matrix is orthogonally diagonalizable, then your matrix is normal matrix. See, this is what the property I am saying. See, orthogonally diagonalizable means what? Eigenvectors are orthonormal or orthogonal. This is what I am saying. I am emphasizing on here. That if your matrix is normal matrix, then eigenvectors are orthogonal, which is saying in the theorem here, and saying this. This is a complex spectral theorem. Okay, so this is an important theorem, and keep in mind. Question would be asked from at least this is a important section of this. Try to do some problem on it. So now he's discussing the proof. Even you can skip the proof because question asks only for So he's what he solved some problem also. This is really interesting. You can see that, and he's generalized that it is for general case Cn. Okay. So my suggestion is week 12. This third lecture is important, and whatever he is solving there, try to solve. I will say to TA that solve some problem on it. This is going to be helpful for to all of you. Okay,
Okay,
clear?
sir.
At least this is clear. This at least
Yes,
this
sir.
one. The next lecture is easy one. The FT is not so tough. Just need to, yeah, this week 12 is not so calculative, but see, this is updated syllabus now. Previously it was so calculative, but now it is easier. Okay, now we'll see tomorrow and discuss the DFT thing, and what is the remaining lecture? DFT and DFT is there. Oh, circular matrix, circular and DFT is there. Which circular matrix? Already all of both of you have seen it already. What is circular matrix? The DFT is nothing but your eigenvectors of, we are calling that as the DFT also. Okay, see it will, lectures is not there. I said to a personal team to update it.
Excuse me, sir.
Yes,
Could you please repeat the last points which you have discussed it now?
this one, spectral, complex
No,
spectral, or
sir.
maybe this
Before
one,
that,
or here this one, this one, or this theorem.
yes, sir. That 2 points. No, sir.
This
The
theorem one,
above one.
ever one, this one.
Yes, sir.
So let me repeat it again. Okay, so I'm saying, let's say I have a linear transformation from Cn to Cn. Okay, here is
Sir,
other assumption. Yes.
means A is a normal matrix if
Hmm.
and only if the eigenvectors are the orthogonals.
Huh.
And then you said in the last that
Hmm.
so this one, that orthogonal diagonalizable if and only if is represented by a normal
Normal
matrix.
matrix.
So
Yes.
I'm not be able to understand these two sentences.
Okay. So here is So orthogonally diagonalizable means, okay. So let's say I have this matrix A, no. So we used to write S D S inverse, right, in the diagonal form, right? Just repeat
Yes,
with
sir.
me so that I will understand. You know, right? This one,
Okay, sir. Okay,
S
sir.
D S inverse. This
Yes, sir.
S is your collection of, or the eigenvector matrix,
Eigenvector.
right?
Yes, sir.
Eigenvector matrix. So here, if your matrix A is normal, no, so he is saying here the word whatever orthogonally diagonalizable is saying, that means your S, which is the eigenvector matrix. This is orthogonal matrix. Orthogonal matrix means what? These vectors are orthogonal to each other. These eigenvectors are orthogonal to each other,
Yes,
and
sir.
that is what it's saying orthogonally diagonalizable. And what I'm here it I'm saying eigenvectors are orthogonal, which is saying to be the same, no, because here is orthogonal matrix means the eigenvectors here, these columns are orthogonal to each other. In different word, it is generally wrote yes, yes transpose is identity. But yes, yes transpose means orthogonal matrix is a matrix is said to be orthogonal means yes and transpose of it. If you multiply, it is identity matrix. In different word, the columns C1, C2, C3 are actually orthogonal to each other. That is what orthogonally diagonalizable matrix. Are you getting it or not? I will repeat it again. No, I mean to say here, orthogonally diagonalizable means I am impacting on this expression. Okay, orthogonally diagonalizable means I am saying about this express. Sorry, this form. And here it says S is orthogonal matrix. If your S is your orthogonal matrix, then it is called orthogonally diagonalizable. Okay, but the thing is that if S is orthogonal matrix, no, so here it means that your columns are orthogonal, but actually columns are our eigenvector v1, v2, v3. That means what it says, eigenvectors are orthogonal. Are you getting it? What I mean to say? Uh, no.
Yes, sir.
Yes, sir. Yes, sir. It is understandable.
I- So that is what it is. Orthogonally diagonalizable means I am saying, our professor is saying this form. This is the orthogonally diagonalizable means. But the thing is that orthogonally diagonalized means this yes is a orthogonal matrix. Okay. But what is the meaning of orthogonal matrix? Means their columns are orthogonal to each other. Their columns are orthogonal to each other. But the columns of yes is actually is nothing but the eigenvectors. Yes is formed by the eigenvectors. So it means
Then
that
S will be
eigenvectors are
normal
also,
matrix.
sorry.
Then S will be normal matrix.
That he is saying if this is happening, then your yes, no, not yes. Your A is normal matrix. If it is happening,
Okay.
then your A is normal.
Okay. Okay. Okay.
If you are able to write your A as in this fashion where S is orthogonal matrix, then A is your normal matrix. It is what it says. It's so many terms are actually coming in the same
Yeah. Yeah.
orthogonal.
Yes, sir.
Normal.
We're
That is
very
why
much
it is very
confused
confusing.
sometimes.
So because of the wording, so no, normal is
Yeah.
also kind of orthogonally. What is there? Sorry, orthonormally is
Could you
there.
please scroll up?
Okay. So the question would be asked up with this case. What is the case? Is that let me create a question on this. Then it will be more clear to you. let's say the question is v1, v2, v3, okay, or maybe v4, whatever, or let's say I'm saying only two. Let's say v1, v2 vectors are given, vectors are given, okay, or v1 and v2 are eigen eigenvectors, eigenvectors of a matrix A. Okay, I'm saying v1 and v2 are the eigenvectors of matrix A. Then what can you say about matrix A? A is symmetric, A is Hermitian, A is normal. Or anything. What way now? Can you tell me? I'm saying so eigenvectors of A and B1 perpendicular to V2 means orthogonal to each other. Eigenvectors and orthogonal. What can you say about it? Can you directly implement it here with this theorem and this one, or from the spectral theorem, or this one? Same thing is there. Means whatever theorem I given, even the same thing is there. Professor is already named it, or spectral theorem, both are same. So what can you say about A? Asymmetric.
The normal matrix.
A is normal matrix. That's all. From theorem you can say. You can say theorem from complex spectral theorem directly. Okay.
If it
This
is
is
a
what
normal matrix, then also it's a Hermitian.
if you no, not necessary. So that is what the next thing. Let me tell you. The interesting thing is that your Hermitian matrix is not sorry. A matrix is normal. The thing. Let me write here simply. Let's say A is matrix. Okay. If A is Hermitian, then A is normal also. A is normal also. If A is symmetric, okay, this is A is normal also. Okay, A is normal also. But this is not the reverse case. Okay, this is reverse case is not true. A is normal, then not necessarily symmetric. Okay, A is normal, then not necessarily Hermitian. Okay, reverse is not true. But if matrix is there, symmetric is there, normal, then A is normal also. Okay, is it clear? This is interesting.
Yes, sir. Now it's clear.
So Hermitian matrices or symmetric matrices are
The rest topic you will cover in next session.
yeah, tomorrow we'll cover the next session because we have almost done 2 hour session. Okay.
5 is not uploaded. What should we do?
We will this is the important. Okay. I already told to ops team here to learn also. Okay. Okay, that's all for today's session. We'll meet tomorrow at 10 a.m. Okay.
Yes, sir.
Okay. Thanks to both of you.